Okay, so I want to start the cardiovascular system by talking about cardiac physiology. Cardiac cells, the excitation, nervous system regulation, and then go over EKGs with you guys. Okay, so cardiac muscle tissue is really cool. You can take the heart out of the chest and it'll continue beating as long as it has nutrients and oxygen. And so these cardiac muscle is different from skeletal muscle and by way that it is automatic. So it contracts without nervous input. So your brain doesn't tell your heart to contract, it just alters the force and rate of contraction. How does it contract? They're actually controlled by pacemaker cells, so bundles of pacemaker cells by the electrical conduction system. And you learned that in anatomy, and we'll cover it again today. It's the extended contraction time. So these cardiac muscle cells, the contractile cells, contract 10 times as long as skeletal muscle. They have a long absolute refractory period. And so because they contract way longer and they have a longer absolute refractory period than skeletal muscle, this is going to prevent wave summation and tetany by those muscle cells. And so what does the nervous system do? Again, it alters contraction, force, and rate. There's two kinds of cardiac cells found in your heart in the myocardial tissue. Remember, myocardium is where you find the cardiac cells. So the first type is pacemaker cells. These guys are autorhythmic and they're myogenic. So they spontaneously, rhythmically depolarize. And these are what you find in your conduction system. So your sinoatrial node, your atrioventricular node, your bundle of His, your right and left bundle branches, and your Purkinje fibers. These guys spontaneously and rhythmically depolarize. They generate action potentials that spread throughout the heart. And this gives way to your heart rate, right? So I want you to understand that electrical events happen before mechanical events happen. Okay, and then the contractile cells get the impulse from the pacemaker cells, and their job is to contract. So these actually have actin and myosin in them so that they can contract. The pacemaker cells don't, these guys do. How do they get the impulse? They get it via gap junctions, right? They both rely on the typical ions that we've seen. It's a little bit different though, and the action potentials look different. So let's take a look at the electrical conduction system. The impulse is generated in a normal healthy individual at the SA node, the sinoatrial node, right? And then it spreads like a wave through the atria and goes to the atrioventricular node. The atrioventricular node holds that impulse for a split second before releasing it to the ventricles. It's going to release it to the ventricles using the bundle of His, right? So it goes through the bundle of His first, and then the right and left bundle branches, and then up the sides using the right and left Purkinje fibers. So notice how electrical current flows through, or action potentials flows through the atria from top and side to the middle, the septum. And then notice how ventricular current flows through the interventricular septum to the apex and then up the walls. Okay, so this allows the atria to contract from the top down and the ventricles to contract from the bottom up. All right, so it helps with functionality of pumping blood where you need it to go. The cells of the sinoatrial node depolarize first, and this is what their action potentials look like. And then they're going to spread through waves to the contractile cells. And notice the contractile cells have the actin and myosin, all right? And then these guys are connected via intercalated discs, and they have little gap junctions or pores that allow the ions to spread through them. So they depolarize really quickly. This generates an action potential that spreads to this cell, this cell, this cell really quickly. Right, let's take a look at the pacemaker action potential. So what do I want you to know for this? First of all, you don't have to get into the voltage. I want you to appreciate that resting membrane potential is around -60 compared to -70 for nerve and skeletal muscle. But take a look at the pacemaker action potential. So you see this slow rise of depolarization, and then threshold is hit and you produce an action potential, right? Slow rise of depolarization, action potential. What are these ions? What does this do to? So if you look at phase 4, it says first it's sodium coming in using these ion channels, and then calcium coming in using transient calcium ion channels, and then long calcium ion channels. So this first part of depolarization is sodium coming in, right? And then calcium comes in to bring it to threshold. And then what brings it to the peak of the action potential? It's actually calcium. And so they're the long calcium channels. So, and draw these out, you guys, just like you did with nervous system. So sodium in, then calcium in to threshold, and then calcium rushes in, producing the depolarization of the action potential, and then potassium brings it back down. You don't have to worry about phase 0, 1, 2, 3, and 4 for these guys. Take a look at the contractile cells. So these contractile cells are sitting really low. They're actually at negative 96. If this was a normal nervous or skeletal muscle cell, it would be way past potassium's threshold, or excuse me, equilibrium potential, and it wouldn't produce a charge. But because it's cardiac cells, the ions are held in different concentrations, and so resting for these contractile cells are actually at 96 millivolts. So they don't get excited really easily. They're really low. As soon as sodium rushes in from the pacemaker cells, bam, depolarize, okay? They're sitting at resting membrane potential. You don't hit threshold, you just go straight through and produce an action potential. So this is sodium rushing in, so depolarization is sodium. And then what is repolarization? Repolarization is potassium throughout this whole thing. So potassium is rushing out throughout this whole thing, right? But look at number 2. This is a plateau. How do we get this plateau in here? The plateau is because calcium is coming in as potassium is leaving. So potassium leaving, potassium leaving, potassium leaving, calcium coming in as potassium is leaving. And so this is going to create a plateau, or it's sort of a, it keeps inside of the cell depolarized longer. This allows you to get calcium into the cell from extracellularly, or interstitial fluid, right? So that the calcium can contract those, so that calcium is available for myosin to contract or to bind to actin, right? Also, this is going to make sure that you have a really long absolute refractory period so that you can't get another action potential, right? Take a look at refractory period in skeletal muscle. So here is absolute refractory period for skeletal muscle, really short. The skeletal muscle is contracting way past that and relaxing way past that. So if you produce another action potential, you're going to get an additive effect, right? You're going to produce a stronger force of contraction. We don't want a stronger force of contraction by way of summation or tetany for cardiac muscle. And so how do we make sure that we don't get a continuous long-term contraction? We make the absolute refractory period really long by having calcium come in. So this is a contractile cell, and look at how long this absolute refractory period is. The myocardium cells have time to contract and almost fully relax before you can get another action potential. This makes sure that these guys don't sum or produce tetany, that the current is going where it needs to go, like the action potential is flowing through the heart the way that it needs to go to get that heart to contract and relax fully before you get another action potential. Here's overlay of the contractile cells, the autorhythmic cells, excuse me, and the contractile cells. So red is autorhythmic, purple is contraction. Take a look at the autorhythmic cells. Notice how they don't sit at resting. So they have this slow leak to threshold, and then they depolarize, produce an action potential, and they just keep repeating it. So they're not sitting there on standby mode. They're continuously, slowly, rhythmically producing action potentials. For the contractile cells, they're sitting really low. They're sitting there at resting membrane potential. They get the ions from the contractile cells. They produce an action potential. And contract and relax. Pacemaker cells are slow to depolarize. They're autorhythmic, right? Contractile cells have a really long absolute refractory period. Both of these make sure the heart works as an effective pump. You want that heart to depolarize, get excited, contract, and then relax before it can contract again, because you want blood to be pumping out to the body, and the heart has to be at rest for a certain amount of time to get blood to flow, or to get the heart to fill with blood. Okay. So what happens when those contractile cells get that action potential? It's just like skeletal muscle, except for that calcium enters extracellularly, and that causes calcium to get released from the sarcoplasmic reticulum. And then from there, it's the same. So the calcium moves the troponin, or binds the troponin, moves the tropomyosin out of the way, so that the myosin head can bind to the actin, and then you get contraction. How does relaxation occur? Calcium gets pulled back into the sarcoplasmic reticulum and kicked out into the extracellular fluid, and then relaxation occurs. So the heart is going to spontaneously, rhythmically depolarize and contract and relax on its own, as long as it has enough nutrients and ions and gas to do so. So how do we regulate it? It's innervated by your autonomic nervous system at the sinoatrial node, atrioventricular node, and the ventricles. Go back to your nervous system notes. So, because I want you to draw this out. So sympathetic nervous system binds to alpha and beta adrenergic receptors, right? Sympathetic nervous system is going to release norepi and epi, and that's going to increase depolarization of pacemaker cells, right? So the sympathetic nervous system is going to excite the heart, so that is going to increase heart rate and stroke volume. Heart rate is beats per minute. Stroke volume is volume of blood ejected per beat. Okay, stroke volume is volume of blood ejected per beat. For parasympathetic nervous system is going to bind to muscarinic cholinergic receptors. So acetylcholine is released from the parasympathetic nervous system. It binds to muscarinic cholinergic receptors, and that's going to slow down depolarization. So when you slow down depolarizations, that's going to decrease heart rate and stroke volume. All right. So make sure you draw this out and know this, because that's really important. Here's a sort of a picture of what it looks like for sympathetic and parasympathetic. So here's a medulla oblongata. Parasympathetic exits your brainstem, and it actually is cranial nerve 10. That's your vagus nerve. That's your major parasympathetic nerve. It synapses with your SA node and with your AV node. If you take a look at your sympathetic nervous system, it exits out of the spinal cord at T1 through T4, goes up the sympathetic chain ganglion and makes your sympathetic cardiac nerve, synapses with your SA node, AV node, and your ventricular myocardium. And so sympathetic nervous system has more regulatory effect over the heart than para. This shows what happens with your fibers, your pacemaker potentials. So green is normal. So notice here's your pacemaker cell. So hits threshold, depolarizes, right? Hits threshold, depolarizes. Take a look at when you add epi and norepi to the heart. So that's sympathetic stimulation. So notice how the slope increases. So it hits threshold faster and produces a faster slope up. So epi and norepi are going to increase. The action potential is generated. Acetylcholine is going to slow down action potential. So it actually takes way longer to hit threshold and generate an action potential. And that is vagal stimulation, which is parasympathetic nervous system. Drugs. So again, I want you to go back to your pictures and look at your drawings, right? So I want you to draw out your, go back to your nervous system notes and your drawings, right? You should have one for your nerve to heart and your for sympathetic and for parasympathetic. So let's talk about drugs for a second. Phenoxybenzamine is an antagonistic drug that binds alpha adrenergic receptors. So phenoxybenzamine inhibits uh, alpha adrenergic receptors or blocks alpha adrenergic receptors. So if phenoxybenzamine is bound to these adrenergic receptors, what can't bind there? Good, your norepinephrine, right? Norepi preferentially likes to bind to alpha adrenergic. Epinephrine likes to bind to beta adrenergic receptors on the heart. Okay. Propranolol is a drug that blocks beta adrenergic receptors so that epi can't bind, right? So what does antagonistic mean? Means it inhibits. So propranolol is going to block that beta adrenergic receptor so epi can't bind, right? So if norepi can't bind and epi can't bind, what's the result? Heart rate's going to drop and stroke volume's going to drop. Good. We have more beta adrenergic receptors than alpha on the heart. And so a way of regulating blood pressure or force of contraction of heart is to give somebody a beta blocker. How do we know it's a beta blocker? Because it ends in OLOL. All right. And so typically you've heard of beta blockers with regulating blood pressure. It's to drop blood pressure when blood pressure is high. Atropine is another drug. It actually is a drug that inhibits muscarinic cholinergic receptors. And so it's found in the belladonna plant. It's a naturally occurring toxin from some of the nightshade family. Tomato and peppers are in the nightshade family too. They don't have this toxin. But atropine binds to muscarinic cholinergic receptors so that acetylcholine can't bind. What does acetylcholine do? Acetylcholine drops heart rate and stroke volume. So it drops depolarization. So if you have atropine blocking that, heart rate's going to go up. Okay. Make sure you understand these drugs, really important, clinically speaking. The electrocardiogram. So the last one is the electrocardiogram. It's a non-invasive way to measure electrical activity of the heart. We put electrodes at specific body locations. We know what normal looks like. Therefore, we can figure out when we see abnormal patterns, and that's going to diagnose damage. It's really cool because your heart, when cardiac cells die, they don't conduct charges. And when they don't conduct charges, the electrical current flows around that damaged area. And because the electrical current flows around that damaged area, the EKG is going to look different. So you know what normal is. This is a really basic EKG lab that we're doing. I recommend to be for your professional programs that you actually take an EKG short course before you get into it. Okay, so normally EKG is a 12 lead system, right? In lab, if we were meeting for lab, we would have put one on the right wrist, left wrist, right ankle, and then left ankle. And these are your chest leads. Einthoven's triangle shows how the heart sits in the chest. It sits in the chest in the mediastinal area, tilted a little bit to the left. It's about the size of your fist. Lead 1 captures electrical current going in this direction, right, towards your left arm, from your right arm to your left arm. Lead 2 captures electrical current going in this direction, right, so this direction of the heart. And then lead 3 captures electrical current going in this direction. Lead 2, the negative is at your right arm, the positive is at your left leg. And so we use lead 2 to analyze the electrical, usually we use lead 2 first to analyze the electrical activity because it's going to show the bulk of the electrical activity, because it's going to show you a picture through that interventricular septum. Features of an EKG. 0 or a flat line represents an isoelectric line. Okay, when your waveform deflects up, that means electrical activity is going towards a positive lead. When the waveform deflects down, it means the electrical activity is going towards a negative lead. So let me actually draw on this. I want to make a note for you guys. Let's see, what is my pen color? Black. Okay, so if we're talking about, let me write it down here, lead 2, right? Here's our isoelectric line, right? Here's our first waveform, our second wave, and then our third waveform, okay? So here's our P wave, our Q, our S, and then our T wave. And I'll go over these in a second with you. Anytime you see a waveform going up, like your P, your R, and T, that means that the electrical current's going towards a positive waveform, okay? Towards a positive lead. Anytime you see a negative deflection, like your Q and S, that means the electrical current's flowing towards the negative lead. If we're talking about lead 2, where's your positive? Your positive is at your left leg. If we're talking about lead 2, where is your negative? Go back and look at the pictures. It's at your right arm, okay? Whoops. And so your P wave, that shows the electrical current going towards the left leg, R towards the left leg, T towards the left leg, Q and S towards the right arm. Okay, so an electrocardiogram, the P wave shows, let's see, atrial, let's do blue. The P wave, I want you to know the basics for lecture and lab. So your P wave shows the atria depolarizing. So P wave is start of P to end of P. This shows your atria depolarizing, right? Your QRS shows your ventricles depolarizing. So right here, QRS shows ventricles depolarizing. And then your T wave from here to here shows your ventricles repolarizing, right? So P wave shows what? Atria depolarizing. QRS shows what? Good, ventricles depolarizing, and T wave shows ventricles repolarizing. If electrical cells depolarize, they need to repolarize. So what are we missing? We're actually missing the atrial repolarization. Why are we missing it? It occurs during the same time as a QRS. We don't see it because the atria are so small compared to the ventricles. The ventricles are so massive that their electrical events overshadow the atria. Another thing that I want to tell you is before the atria depolarize, what starts depolarizing? Okay, so we have SA node depolarizes for a split second, and there's no movement of that action potential, so we don't see anything on the EKG. Then it's the atria depolarizing. Then the AV node, and there's not much room here, sorry, AV node, and then the ventricles depolarize. This is actually the, this is the bundle of His, your bundle branches, and your Purkinje fibers. I don't want you to know that for the exam, but just so you have an idea. And then this is your ventricles repolarizing. So this whole time period, you had to actually label, label your EKG. So some of the things that I want you to label, or what I want you to label first on your resting, and you can do it on your post exercise so that you have experience labeling them. I want you to label your P wave. So your P wave is start, where the P wave starts going up to where it comes back down to baseline. So that's your P wave. Your QRS is start of Q to end of S. I know it's kind of hard to do this, sorry. And then your T wave is start of T to end of T when it comes back down to baseline. Your PR interval. PR interval is start of P, right? So start of P to start of Q. Why do we call it PR? Because sometimes, usually you can't see the Q, and so it's PR. This is your PR interval. And then the whole thing from the start of P to the end of T is your PT interval. Why do we call it an interval? Because it has waveforms in the calculation. If there are no waveforms in the calculation, we call it segment. If there are waveforms, it's interval. PT interval actually is when your heart's contracting, so it's systole. Your T to P segment, so this would be your TP segment, this is diastole. What does diastole stand for? It's when your heart is at rest, right? Good. So it's when your heart's at rest. So, and I want you to be aware of that the EKG shows electrical events only, so it's not going to show mechanical contractions, but we can assume that systole is from, or contraction of atrium ventricles are from P to T, and then the atrium ventricles are relaxing from T to P, okay? And this is the second waveform. Notice that this takes 800 milliseconds. So if you look at the EKGs, contraction should take about 0.4 seconds or 400 milliseconds. And then at rest should be about 0.4. When we start exercising, we have to increase the action potentials per minute. How do we increase that? We actually shorten diastole. So we shorten the time that the heart's at rest. So you'll notice if you look at your after exercise or your post-exercise EKG, that systole is relatively the same amount of time because, again, you're generating action potential. It's going through your conduction system, but diastole shortens the amount of time at rest. Okay, so I want you to take a look at this and correlate the EKG with the electrical flow through the heart. It's a really, really basic animation, but it's a really good animation. So right before the P wave starts, that's the SA node depolarizing. So SA node depolarizes right about in this area, okay? Then the P wave is the atria depolarizing. Whoops. The PR interval shows the AV node through, or sorry, the SA node through the AV node. So this shows SA node through AV node. The AV node actually holds the impulse for a split second before it releases it to the ventricles. The QRS is your ventricles depolarizing, right? And then your T wave is a ventricle repolarization. Systole is from P, right, to T. So systole is, let's put a note by this. So P, is it PT segment or PT interval? Good, it's PT interval because you have waveforms in the measurement. Diastole is when the heart's at rest. What is that? So diastole is from end of T to the second P. So this is TP segment. Okay. Systole means contraction. Diastole means relaxation. When the heart's contracting, it's going to give you your systolic blood pressure. When the heart's at rest, it's going to give you your diastolic blood pressure. So that's where we get systolic and diastolic blood pressure from. You don't have to worry about all the other stuff. So notice how ST interval, we're not going to worry about that. I know they're relevant at QT interval, they're relevant clinically, but I want to make this really easy for you guys to understand. So don't label the whole kitchen sink, okay? Focus on what I asked you to label. And then make sure you spend time labeling that because that's worth 4 points for your lab. All the rhythmic cells, your SA node depolarizes the fastest. So it generates about 70 to 80 action potentials per minute. AV node generates 40 to 60 action potentials per minute. Bundle of His and Purkinje fibers, about 20 to 40 action potentials per minute. This correlates with beats per minute. So the SA node depolarizes at 70 to 80 action potentials per minute. That's going to give rise to 70 to 80 contractions per minute, or that would be the heart rate, okay? How does this work? The fastest cells are going to be the pacemaker for the heart. They're going to set the rate for the rest of the heart. So which one is a pacemaker? Good, your SA node is going to be the pacemaker of your heart in a normal healthy individual. Sometimes SA node has trouble firing. People can, they can put in a pacemaker, mechanical pacemaker, so that it fires and generates action potentials for the heart. They can cardioconvert or stop the heart and start it again, or let it start on its own chemically, or they can cardioconvert electrically with paddles. If the SA node is damaged, though, what takes over as pacemaker of the heart? Good, your AV node. And in that case, if SA node is damaged, would you see a P wave? No, you wouldn't. And so the AV node is going to take over as pacemaker. What if AV node is damaged? What's going to take over? Good, bundle of His. Can this sustain life? Not for very long. Okay, bundle of His and Purkinje fibers can, but not very long. Can you go without your SA node, or can you survive without your SA node contracting your atria? You actually can, because atria, the ventricles are below the atria, and so they get blood from the atria just because they're below the atria. And the ventricles are ones that contract and pump blood to the body. So you can survive without the atria contracting, but you can't survive without the ventricles contracting. Okay, so this is what you did for labs. So first you labeled your P, QRS, T, your PR segment, your QRS interval, or excuse me, your PR interval, your QRS interval, systole and diastole, okay? So let's go over the 5 rules for interpreting EKGs. The first rule is rhythm is regular. So what the heck does that mean? You wanna look at the EKG, and there are more specific ways for doing this, but you wanna look at the R waves, right? So here is your, sorry, let me draw this for you. Here's your P wave, right? So here's your P wave from here to here. Here's your QRS, and then here's your T. Here's your second P wave, QRS, T. You can tell the T's compared to the P's because P's are always small because they're the atria. The T's are always going to be the ventricles, so they're bigger. All right, so you're looking at your R waves. I don't want to draw too much on this because it's going to muck it up. So here are R waves. So you want to look at your R waves. Do they look like they're normal intervals? They do on this one, okay? So this would be a regular rhythm. You can use a caliper to adjust and measure from R to R. You can use a ruler, you can use an index card, and put a line here and put a line here, and then put it over the various ones and make sure that it follows the rules. But this rhythm looks regular. Resting heart rate is 60 to 100 beats per minute. How the heck do we do that? Okay, so in order to do this, you need to understand that from, say this is our 0 mark, the big line, and then this one, and I'll try to be really careful. This one is 0.2 seconds. That one is 0.2 seconds as well, right? 0.2. So each big box is 0.2 seconds. So this is 0.2, 0.4, 0.6, 0.8, 1 second, right? This is 0.2, 0.4, 0.6, 0.8, 2 seconds. Whoops, 2, 4, 6, 8, 3 seconds. Okay, so this is 3 seconds worth of data. In order to do the 3-second method, you need 3 seconds worth of data. You're going to count the number of R peaks you see in the 3 seconds and multiply that by 20. How did I get 20? 3 seconds times 20 gives you 60 seconds, right? And beats per minute is beats per minute or beats per 60 seconds. So I'm measuring out 3 seconds worth of data. And how many R's do I have? I have 1, 2, 3, 4 R's, right? So 4 R's times 20 gives us what? 80 beats per minute, okay? Whoops. We could do 6 seconds worth of data. So 3, 2, 4, 6, 8, that's 4. 2, 4, 6, 8, 5. 2, 4, 6, 8, and 6. Whoops. So how many R's do we have in 6? So we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 R's. And we're multiplying it by what? Good. So by 10 to get 80 beats per minute. Whoops, I did it again. 6 seconds times 10. How did we multiply it by 10? Because if we have 6 seconds worth of data, times 10 is going to give us 67 seconds, or extrapolate 60 seconds. So if you think about it, we're counting how many beats there are in 6 seconds and extrapolating it to 60 seconds. So that's why we have to multiply it by 10. If we're doing the 3-second method, we're counting how many R's or how many beats there are in 3 seconds, multiplying it by 20 to figure out how many are in 60 seconds. The third one is really easy. It's P to QRS ratio, so it should be 1-to-1. What does that mean? For every P wave, there should be QRS that follows. So let's look at the first one. So the first one, let me see if I can change my pen. Not working. Okay, so okay, so that let's do green. Okay, so I don't know if I like that either. Okay, so for every P wave, there should be a QRS that follows. So here's a P, here's your QRS. P, QRS, P, QRS, P, QRS. So this EKG would be a 1-to-1 ratio. What does that mean? That means that the SA node and the AV node are in communication, okay? We'll go over the abnormals in a second. The last two are just measuring it. So PR interval should be 0.12 to 0.2 seconds in duration. QRS interval is 0.04 to 0.1. So let me show you, I think I forgot to show you the itty bitty boxes. So let me do the itty bitty boxes. So if you look at the 0 mark, do you see how we have itty bitty boxes in here? It's actually kind of like the hemocytometer. So we have 5 itty bitty boxes. So 5 itty bitty boxes. To get 0.2, those 5 itty bitty boxes have to be 0.04. So this itty bitty box, let me see if I can do this, is 0.04 seconds in duration. So that itty bitty box is 0.04 seconds. So this is 0.04, excuse me, 0.04, 0.08, 0.12, 0.16, 0.2. All right. So what you need to do for number 4, your PR interval, you actually have to measure it. So let me write it in a different color. I'll do the blue one so you can actually see it. So you're gonna, and pick one that's on the line to make it a little bit easier. Let's see. It looks like this one is closest. Okay, so we'll say P starts right here. So here's your P wave and here's your R, right? Whoops. How long is that? So that's 0.2. Okay, does that fall? Let me write it down for you. Does that fall within your rule? It does. So PR interval is 0.12 to 0.2. So this PR interval is 0.2. So that works. Okay, it's actually showing communication from SA node through the atria to AV node. Then your QRS interval should be 0.04 to 1 second. If you take a look, let's do it on a different one. This one looks like it's almost on the line. So here's your QRS interval, right? It looks like it's 1 box. So this would be 0.04, or 2 itty bitty boxes, which would be 0.08. So if you take a look at this one right here, this one looks like it's 0.08. That one looks like it's 0.04. That one looks like it's 0.08. That one looks like it's 0.08. Okay, these guys should be 0.1 or less. So not much bigger than 2 itty bitty boxes. Okay, and so I hope that this helps you figure it out. What I want you to do for lab is I want you to first label the waveforms. So PQRST, then your PR, interval, then your QRS interval, then your PT interval and TP segment, your systole and diastole. I want you to label your seconds. So your 0.2, your 0.04, right? Your 0.2 and 0.04. And then your voltage from here to here, one box is actually 5 millimeters or 0.5 millivolts. Label that all first for your resting and your post exercise. And then I want you to go through and I want you to fill in the chart. So I actually want you to measure the duration or the time that each one of these takes. And so I recommend you printing these out and labeling them. If you have a printer at home, or you can draw on the pictures in lab and save them that way, so that you can understand how to do this. You will see these again. So you will have EKG strips to identify for lab. For lecture, I want you to understand the rules, understand what your P wave, QRS, T, systole, and diastole are. Again, look at your review sheet, right, for this exam so that you know what you should be studying. Let's look at some abnormals. Okay. I am not going to go crazy with abnormals, but just so you see a little bit. So the top one is normal sinus rhythm. So this is a normal sinus rhythm. So it's generated SA node depolarizes the atria, AV node depolarizes the ventricles, and then the T wave, and then that rest, and then contraction, relaxation, right? Contraction, relaxation. Here's tachycardia, and so this is with an inverted T wave. Look at your EKG. Your resting is normal sinus rhythm. Exercise is tachycardia. It's not abnormally fast. It's what you would expect with exercise. And then bradycardia is slow. Okay. First degree heart block. First degree heart block means that it's not as severe. It's the least severe out of the heart blocks. It means that all the atrial impulses are conducted to the ventricles, but there's a slowed conduction through the AV node. So because the AV node is slightly damaged, impulses are still getting through. They're just not getting through as fast as they normally would. So your PR interval is greater than 0.2. It's taking longer to get through there, so PR is greater than 0.2. Here's normal, right? So here's your SA node through the atria, AV node, ventricles. Take a look at somebody who has a first degree heart block. So here's your P wave, and then look at how long it takes to get through that AV node. The impulse is still getting through that AV node. It's still depolarizing the ventricles, but it's taking way longer than 0.2. Remember, one box is 0.2, and so this is taking about 0.3 seconds to get through. So that's a first degree heart block. Second degree heart block is a little bit more severe. Some of those impulses are getting through to the AV node, but some of them aren't. Because that AV node is more damaged, you lose that one-to-one relationship between the P and QRS. Okay, and you lose that one-to-one relationship between the atria and ventricle contraction. So look at letter A. Here's your P wave, and then your QRST. P wave, QRST. Do you see how this is within your PR interval is within 0.2, but look at how it gets longer. So it's taking longer to get through that AV node. There's damage there. And so here's your P, here's your QRS, here's your P, here's your QRS. These are abnormally long. And then take a look. Here's your P wave. Did it go through the AV node to depolarize the QRS? It didn't. And so that shows that that AV node is more severely damaged. And then here's your P, QRS, P, and it's getting longer. And then here's your P wave, no QRS. And so you're losing that one-to-one relationship. So you should see one P wave and then a QRS should follow it. One P wave and then a QRS should follow it. With a second degree heart block, you don't always see a QRS right after that. Third degree heart block is where that AV node is completely damaged. So you've lost conduction through that AV node. So the SA node is depolarizing the atria, and then the bundle of His is depolarizing the ventricles. And so what you see is, notice how that P wave is faster, and then the QRS is depolarizing slower, and it's depolarizing independently of the atria. So atrial and ventricle contractions are independent of one another. And this is really dangerous because if they're not coordinated, it's not pumping blood effectively, and there's mixing of blood, and that could ultimately cause blood clots to form because it's not normal laminar flow. Abnormal pacemakers, ectopic pacemakers. Sometimes your heart throws random action potentials or irregular rhythms. Irritable cells produce random action potentials. These can generate a high rate of action potential. They're really dangerous because they bypass your normal conduction system, and they can actually disrupt or stop ventricular contractions so that the ventricles quiver. Let me give you an example. Let's say you've had the flu and you're severely dehydrated. Your ion balance is off, and so your cardiac cells are irritable, and they can randomly generate action potentials. You see this with cardiac arrest. So sometimes you hear of high school football players collapsing because their heart, they went to cardiac arrest. This can happen. This can cause cardiac arrest, right? So you want to be careful, make sure that your athletes, or if you're doing, a marathon, that you're exercising effectively, that you've cardiovascularly trained yourself, that you are not dehydrated, that you have enough ions in your plasma, your calcium, your magnesium, potassium, sodium, so that you're not, the likelihood of producing an ectopic pacemaker is unlikely, so that your heart doesn't stop. What ends up happening with cardiac arrest is the heart quivers, and it affects ventricular contractions. And so when the ventricles are quivering and those cells are spontaneously non-rhythmically depolarizing, you're not getting a contraction. And so what ends up happening is you need an AED device really close so that you can shock the heart, so you stop the heart, and then you allow the SA node to start taking over as pacemaker. And so you can either chemically cardioconvert or you can electrically cardioconvert with paddles. That's why AED devices are so important in areas of work, schools, where they're having sporting events, because you only have a couple of minutes to shock that heart and hopefully allow it to take over normal sinus rhythm. Okay, this is atrial fibrillation. So this bottom one shows atrial fibrillation. Irregular fibrillation, or waves between heartbeats. Rhythm is irregular and erratic. They'll try to control this with an alpha blocker, like let's say verapamil, or something that's going to regulate this. They can cardioconvert it, so you can go in, they'll put you to sleep, they'll electrically shock your heart so it stops, and then try to get it back into normal sinus rhythm. This is, your heart feels like it's fluttering in your chest, but it is not a life ender usually. In the case of ventricle fibrillation is really dangerous because the ventricles, you've lost that coordination of electrical activity of that heart, of those ventricles. When those ventricles flutter, you're not getting any blood kicked out to the body. And so death can ensue within minutes, right? So you need to get on that. Okay, so I hope that this made the EKGs a little bit clearer. I have office hours this week, so contact me, send me an email, let me know. I know that they are complicated. Spend some time on the lab. I know the lab's taking some time, but again, we're getting into regulatory processes, and we're looking at whole body systems, and we're regulating homeostasis. So this is where the material gets a little bit more complicated. But I'm here for you, and I will see you soon. Thanks.